C++26 is upon us. And with it comes stood execution, a generic framework for modeling asynchronous computations in C++. But this is not the first time an effort has been made to model asynchronous operations in C++. Efforts to do this extend at least as far back as the release of Asio in 2003. Thereafter, Asio was reshaped into the networking TS and proposed for standardization. It became intertwined with P0443 unified executors, but then this thread of standardization died out. Stood execution appeared on the scene, and now it has gone the whole way, being voted into the working draft of C++26 last year in St. Louis. Which leaves us in an awkward position. We've now adopted something into the standard that is different than the de facto industry standard for the last 2 decades or more. Which leaves us with a question. How are we going to adopt the new thing? We have 20 years of code written under the new model. We're not going to go out and rewrite all of that proven, tested, deployed, working code just because the standards committee took a vote. But at the same time, there are compelling reasons to use stood execution. We want to take advantage of those. So how do we reconcile these two things? What if we could have our cake and eat it too? What if we could start out writing a program that looks like this? A form familiar to everyone who's ever written an Asio program. They've probably inferred by now that we are writing a program which submits an HTTP request and reads the response thereto. But what if the familiarity to people used to writing Asio could end there? What if we could just bootstrap on top of this functionality that we've had for 2+ decades and turn around and just start writing stood execution code? Say we want to perform a sequence of operations. The first operation, of course, is to resolve some hostname and to do so in a way that looks familiar to people used to Asio. But the embedding of this is unfamiliar. It's now embedded inside of stood execution, and we can take advantage of stood execution and say that after we resolve the address, we want to turn around and we want to connect our socket. With our socket connected, of course, we need to write the request there too. And thereafter, we're going to need to loop to read the entire body. First, reading some bytes into our buffer, and then maintaining the buffer and deciding whether or not we're finished looping. But before we decide whether or not this story is plausible, maybe we should actually understand senders and receivers at Asio. Understand the two ecosystems we are discussing. And to do this, I actually want to begin by discussing neither of these. I don't want to discuss senders and receivers or Asio, but instead the humble synchronous function call, something we all know and love and understand. Of course, at the core of this model is a function, but a function doesn't do anything on its own. It's simply a latent collection of instructions. In order for it to do anything, it needs to be brought together with a call site, somewhere from which it is called, from which the ability to make forward progress may be delegated. But this is insufficient. This synchronous function requires some space in which to perform work. It requires a stack frame to store all of the variables it has with automatic storage duration. But this is just data layout, and the point of a function is to actually do something, and so we need to move to the moment whereat the ability to make forward progress is delegated thereto. The function runs to completion. It returns the results through to the call site from which it's called, completing the cycle on the diagram. But there's a problem with this formulation. In regular C++ function calls, we actually can't observe the difference between these bottom two entities. We just write a function call, and atomically, from our point of view, a stack frame is allocated, and we jump into the function. But this conceptual decomposition still has value, as we're going to see in a few moments. For the time being, let's look at an example of a synchronous function, something anyone who's ever written low-level I/O is probably familiar with, stitching together partial reads into one total complete read. But this is not a talk about I/O. The particularities of this function are not germane to this talk. Let's focus on what's important here. We receive a parameter and it is reified as a variable with automatic storage duration. Then we can make use of it freely throughout the remainder of the function without worrying about whether it is within or without its lifetime. We can assign to it over and over again. We can use it as scratch storage to effectuate our operation. Now let's consider Asio. At the core of the Asio model is an initiating function, a regular synchronous function with a special property. The special property is that upon the successful completion thereof, there is an asynchronous operation outstanding in the background. But this formulation implies that we can complete the operation after the return from the synchronous initiating function. And so simply selecting a call site is not sufficient. We need to bring the initiating function together with a completion handler, an invocable it can invoke to pass all of the value synthesized by the operation. With these two brought together, the result is an asynchronous operation, which upon its completion, of course, invokes the completion handler. But this diagram looks dissimilar from the one we just saw for the synchronous domain. We are lacking that free local storage as an endemic part of the model. But then we remember that synchronous functions also hid this storage from us. It was hiding behind that lexically atomic allocation of the stack frame and jump into the function. Maybe the same is the case for Asio as well. Maybe this free storage is just hiding inside of the model, but alas, that's not the case. Asio actually lacks this, and as we move on to an example Asio function which does exactly the same thing the synchronous function we reviewed earlier does, we can see this if we focus only on the parts of the code that are important. We can see that I capture the span in a lambda, I declare that lambda mutable, and then I repeatedly modify that member of the lambda. The lambda is moved around into successive operations. It's not stable in memory because Asio lacks this property synchronous functions have. Enter now stood execution. At the core of its model is a sender, the asynchronous analog of a fully curried function. But just like a function, it doesn't have motive force on its own. It can't make forward progress until it's brought together with the context to which it reports its completion, a receiver. Hence the colloquial name of this model, senders and receivers. A sender and a receiver are connected, and the output of that operation is an operation state. This is the asynchronous analog of a synchronous stack frame, local stable storage the operation can rely on throughout its lifetime. But critically, unlike the synchronous domain, we can independently observe the allocation of this storage. When we call connect and we get back an operation state, we are under no obligation to start making forward progress on the asynchronous operation represented thereby. Instead, we can defer this for any amount of time we desire, but once we call start on the operation state, an asynchronous operation results. It drives through to completion, and it sends a completion signal to the receiver. In keeping with the pattern we've established heretofore, we can, of course, observe a senders and receivers implementation of read. But once again, the exact particularities of this code are not germane for our purposes. Instead, we merely look at what we care about. We see that I use let value to allocate a span inside of my operation state. This reference is guaranteed to be valid for the remainder of the asynchronous operation, and so I can use it with confidence in a way that is not just similar to the synchronous domain, but is lexically identical thereto. Now that we understand these two models, we can consider the fundamental question of this talk. How can we integrate these two together? As we think about the example that we saw earlier, we were calling Asio operations from stood execution. So maybe we should start this with the stood execution model. A sender and a receiver and an operation state, but ones which have a special structure. When we call start on the operation state, it synthesizes a completion handler, passes it to an initiating function, and of course, in accordance with what we understand about the Asio model, the result is an asynchronous operation. It completes and invokes the completion handler, but we selected the completion handler. We synthesized it, and so of course, we implemented it to send a completion signal through to the receiver. Let's take a stab at reifying this in code. Let's write a factory which makes an Asio sender and accepts the initiation. A unary invocable awaiting only the selection of the completion handler. In accordance with what I said about senders being fully curried versions of synchronous functions, we of course just curry the arguments into a sender and we return it. This of course raises the fundamental question of what exactly is inside that sender, and so we peer inside that as well. We see that it opts into the concept's machinery of stood execution by providing the needful nested type alias. It, of course, has a data member for the initiation it is currying, and then it's connectable to a receiver. It has that fundamental basis operation of a sender. But this just reorganizes our data further. We now take our initiation and the receiver, and we put it together into an operation state, and we return that operation state via C++17 guaranteed RVO. Bringing us, of course, to our next question, what does that operation state look like? It opts into being an operation state, once again through a needful nested type alias, and now has 2 data members instead of just 1. Then it has the fundamental operation of an operation state, start, the thing that causes asynchronous forward progress to actually begin. We go and we invoke the initiation and we provide it with our completion handler, which of course takes all of the values synthesized by the underlying Asio operation and forwards them perfectly down the value channel to the receiver, thereby completing the operation. I've been up on stage for less than 10 minutes, and apparently we've already married Asio and stood execution. But then we look at this code further. We notice something curious. I've declared this function no accept, but initiation is something I accept generically. I didn't establish any properties thereof. I didn't check to see if I could invoke it without throwing exceptions with my completion handler. This implementation can throw an exception and cause to terminate, which is decidedly unergonomic. And you might think to yourself, well, of course, we will just strike the no accept or we will make it computed. But this is not a workable solution either. Start is the point whereat you transition from the synchronous domain to the asynchronous domain. Synchronous reporting mechanisms become unavailable to you. Synchronous reporting mechanisms such as, for example, throwing an exception. It is incumbent upon the implementation of Start to use only asynchronous reporting mechanisms such as, for example, catching its own exceptions and directing them down the error channel to the receiver. But while we've solved one problem, this raises another problem. Previously, our wrapper had a nice property. It completed in exactly the same ways as the underlying Asio operation. But now we've gone off and we've added a new way in which it can complete through the asynchronous analog of a synchronous throw. How do we document this and expose this to our users generically? After all, our understanding of the asynchronous domain heretofore has been rooted in the synchronous domain, and synchronous functions have a function signature. We can look at it and we can see the values, if any, returned thereby, and we can tell based on whether or not they are annotated no except if they have an error channel and can throw exceptions. And so, of course, being a generic ecosystem, stood execution has a solution to this. You document the ways in which your operations complete by instantiating stood execution completion signatures. Here we can see an instantiation which communicates that the corresponding operation completes, successfully transmitting a single integer and erroneously via the asynchronous analog of a synchronous exception throw by sending an exception putter down the error channel. But instantiating a class template doesn't get us anything. What we actually want is that association. And so now we discovered that we haven't completely explored the interface surface of a sender. Because senders also need to document the ways in which they can complete by providing the const eval static member function get completion signatures, whose return type documents the way in which the corresponding operation would complete. But as we look at this, we haven't satisfyingly answered the question here either. I've elided the template argument list of stood execution completion signatures and replaced it with question marks. And this is because of the formulation I laid out earlier. We complete in all of the ways the underlying Asio operation completes, plus set error with an exception putter, which raises the question of how do we generically discover the way in which the underlying Asio operation completes in turn? And the answer to that is the same as the answer in this domain. When we looked at an Asio initiating function earlier, it wasn't actually a doctrinaire conformant Asio initiating function because it directly accepts a completion handler. And so in order to make it conforming, make it what people expect when they're participating in the Asio ecosystem, we need to perform a change of variable. We need to rewrite the function signature, so rather than accepting a completion handler, we accept a completion token. But this transformation on its own hasn't really gotten us anything, as we can see by examining the code. We now have a use of H, but we've never declared H since I got rid of it. And the reason for this is because adding a level of indirection is insufficient if you don't actually go through the indirection. Accepting something that should be resolved via a customization point is useless if you don't defer to the customization point. And in this case, that is async initiate. And immediately we notice something. Async initiate, our customization point, receives the logic by which our operation is initiated as a lambda. It can determine where and when and how it invokes this lambda, and therefore where and when and how it begins the asynchronous operation. But something else has happened too. We've received a declaration of H, but more importantly, this declaration flows from the implementation of async initiate. Whoever is on the other side of that customization point not only gets to select how the operation begins, but also how it completes. But we've gained more from this transformation because we've customized the initiating function in another way. We've customized the value that it returns, and we've allowed async initiate to select that as well. We are no longer married to a returning void. And lastly, in our journey through this transformation of our initiating function, we have forced the author of the initiating function to document generically all the ways in which their operation can complete. And so now we need to reformulate our understanding of how we're going to adapt Asio and stood execution to account for this, to use these completion tokens which allow us to so completely customize Asio operations. And so we return to our diagram of the Asio ecosystem and we update it with this new understanding. We now understand that initiating functions don't accept completion handlers. They instead accept completion tokens. And we understand the completion token is able to customize every element of the initiating function. And so we imagine that maybe the completion token we suggest so completely customizes the initiating function that it is induced to return a sender. And if it does this, of course, we just get the rest of the stood execution ecosystem for free. So let's take a stab at doing this. Let's declare a completion token type and an instance thereof for convenience. But as I said earlier, this gets us nothing if we don't actually go and provide the implementation on the other side. And so we specialize async result to provide our implementation. We see at the very top of the slide that we're getting that critical information we were missing earlier. We are receiving all of the signatures, documenting generically all of the ways in which this Asio operation completes. Moving into the static member function, we see we receive the initiation, the instance of the completion token selected, and arguments that need to be curried into the initiation. And so dutifully, we perform this currying. We formulate F, which curries the initiation down to a unary invocable, awaiting only the selection of the completion handler. Thereafter, we once again curry our arguments into a sender, but that sender is enriched by transforming the Asio signatures to the form expected by stood execution. We provided that vital context it was missing earlier. But this raises a bunch of questions. There's a bunch of code we're going to have to modify in order to make this work, such as, for example, providing the template metaprogramming necessary to transform those signatures. At the top of the slide, you can see the transformation for each of the Asio signatures, which simply changes the return type of the function type from void to stood execution set value t, thereby documenting in the stood execution domain that this is a successful completion. At the bottom of the slide, we apply this transformation to all of the Asio signatures, and then, of course, critically, we append stood execution set error t of stood exception putter, since we are enriching that set with the asynchronous exception throw that started us down this path. Now we need to walk through our code and we need to update it with this understanding. We need to provide get completion signatures on our sender, but we also provide a constrained version thereof. Recall in connect, we need to propagate the initiation from the sender into the operation state. There are certain CV and ref qualifications with which this may be impossible. Imagine we have an initiation, but that initiation is only movable. But someone tries to L-value connect our sender, which would require us to copy the initiation. This is clearly impossible, and so we detect this scenario here and we neglect to produce completion signatures in this instance. Carrying on in this vein, we move on to connect, which still accepts the receiver and still moves data through to the operation state, but is now constrained to require that the provided receiver be able to accept all of the completion signatures we emit. But notice something subtle here. I determine the completion signatures we emit by deferring to stood execution completion signatures of D. This in turn tries to evaluate the function I just showed you on the preceding slide, thereby transitively pulling in all of the constraints thereupon. Which brings us back to the operation state, which remains undisturbed by this transformation. We stare at it for a while, and maybe we notice something else. Maybe we decide to think about the question that set us down this path from the opposite point of view. Earlier, we were concerned that the initiation might throw an exception, and this might call terminate because we were throwing into no accept. And so we added this unconditional try catch. But what if our consumer is providing an initiation they know never throws an exception? Now we are requiring them to provide an error channel on the receiver that they know will never be taken. But then we realize something. We take a step back and think about what we're doing, and we realize that we are obsessing over the initiation of an asynchronous operation. In some sense, that is the least interesting part of an asynchronous operation. We reach for asynchronous operations because we want the asynchronous parts that run in the background. And so maybe if the asynchronous parts running in the background can throw an exception in the Asio model, we don't need to worry about this question. It's irrelevant whether or not the initiation throws if the asynchronous parts are always liable to throw an exception, and therefore we're always liable to send set error with an exception putter. And so we go back and we look at our initiating function for read. And we notice that the asynchronous part, which runs at the completion of each asynchronous read, is just regular C++ code. This isn't some sub-language of C++. Any C++ code can be written herein. And so maybe I look at it and I look at my use cases and I decide these completions that are erroneous, they're actually exceptional. I don't want to model them with error codes. I want to be a doctrinaire C++ programmer and, of course, render them as the exceptions they ought to be. But now we have a problem. We have an issue. For initiating functions and regular synchronous functions, we understand very well what happens when we throw an exception. The exception is, of course, propagated to our caller. But now we're throwing an exception in the asynchronous part of an asynchronous operation. Who is our caller? Who sits above us on the call stack? Who are we throwing this exception to? And the answer to that lies in the way in which Asio obtains the ability to run asynchronous parts. It lies in executors, the place the asynchronous parts of operations run, a policy by which that may be obtained. And so now we need to understand what's actually happening here. We need to understand how the executor or the execution context that underlies it actually gets the ability to make forward progress. Because as we reviewed earlier, the ability to make forward progress needs to be delegated to something. It doesn't just appear out of thin air. So let's consider a simple example where we try to initiate a single asynchronous operation directly from main and drive it through to its completion. Of course, we know that in the Asio model, we need to get the operation started, and so we call the initiating function, which is just a regular synchronous function. We understand well what would happen if this threw an exception, but let's imagine it succeeds. It succeeds, of course, and returns, and there is an asynchronous operation outstanding in the background. But what does that actually mean? It's outstanding where? Who's going to run it? What do we need to do in order to induce it to complete? And the answer to this in most Asio applications is that we need to go to the execution context and we need to delegate the ability to make forward progress there to. We need to call run thereupon. Internally, run has special structure such that it waits for asynchronous parts to be ready to execute and executes them. And so, of course, it is run which invokes my completion handler. When I throw an exception from my completion handler, it is thrown to run, and it is handled by run in accordance with whatever policy that execution context and executor provides. It may simply neglect to run the operation any further. It may do something else entirely, but unfortunately, this formulation doesn't mesh with the requirements of stood execution. Stood execution brings us something known as structured concurrency, the asynchronous analog of structured programming. And just as you wouldn't expect calling a function in your code to cause execution to jump to some other unrelated part and resume there and never return from the function, so too when you initiate a stood execution operation, that operation is required to report completion to you at some point. But this formulation I've just laid out of exceptions being handled in an executor specified manner doesn't mesh with this. Forward progress can simply be abandoned. Completion can never be reported because Asio implements what is known as unstructured concurrency. And so now it is incumbent upon us to figure out how we are going to layer the guarantees of structured concurrency on top of this, how we are going to implement it in terms of unstructured primitives. Let's return and look at our call stack. The completion handler is throwing to run only because it is run that invokes the completion handler. What if we can inject some logic here? What if we can inject our own call frame, our own wrapper lambda around the completion handler? Then we would be able to handle any exceptions thrown thereby in any way that we want. We could direct them through to the receiver, send them down the error channel thereto. And in fact, we could turn around and we could say that we are the ones implementing an executor, and this is the executor specified way in which we handle exceptions. We handle exceptions satisfying the guarantees of structured concurrency. But of course, this confronts us with a problem. In order to actually do this, we need to write a P0443 style one-way executor. And so we start doing that. Our executor has two members. Of course, it has some reference back to the operation state because that's where the receiver lives. And then it wraps the underlying executor because we're not interested in customizing all of the ways in which asynchronous parts execute, just this one particular way about how exceptions are handled. P0443 style executors must be comparable, and so we provide operator equals equals. Which brings us to the fundamental operation of a P0443 style one-way executor, the unary member function execute, which receives a nullary invocable and invokes it somehow. Invokes it in accordance with whatever policies are embodied by this executor. And so, of course, the simplest implementation is to simply defer to the executor we're wrapping. But then we remember something. We have no guarantee that calling execute on our inner executor doesn't throw exceptions. The whole reason we're doing this is to catch exceptions and direct them down the error channel of the receiver, and so we do exactly that. But then something else occurs to us. The executor underlying us embodies whatever execution policy it embodies. We know nothing about it. Maybe that policy is to take the work and place it on a queue and later dequeue it and invoke it somewhere that's not underneath us on the call stack. In that instance, this catch will not catch exceptions thrown thereby, and so it's insufficient to wrap on the outside. We also have to intrude inside execute and wrap therein as well. Of course, this is insufficient to fill out the required interface of a P0443 style one-way executor, but none of that is germane to this talk, and so I'm going to simply avoid it. For now, we need to concern ourselves with how this class we've just written actually gets injected into the Asio ecosystem. How do we tell Asio it needs to use this to invoke the asynchronous parts of our operation rather than any other executor it was going to choose anyway? And the answer to this is that we need to write an associator. We need to associate our completion handler with a strategy for obtaining an executor so we can customize it at every level of analysis. Earlier, we saw something akin to this when we specialized async result to provide an implementation of async initiate. And so now we specialized associated executor to provide an implementation of get associated executor. But we see that this requires a completion handler type we can speak, which is something we're going to worry about in just a moment. For now, let me draw your attention to the implementation of get. We take in our completion handler and whatever fallback executor Asio was going to use anyway. We wrap both of them up into our executor and return it, thereby causing Asio to customize the way in which it invokes asynchronous parts at every level of analysis. We've now succeeded at catching all those exceptions and redirecting them through to our receiver. Of course, this requires us to have a completion handler type we can actually speak, and so we go ahead and do that. We extract the body of the lambda we were using into the function call operator, we provide a pointer back to the operation state, and then, of course, this would be useless if we didn't turn around, look at our operation state, actually take that lambda and replace it with our completion handler. As this completion handler syncs into Asio, it now carries along with it the customization we just defined. Asio is induced to use our executor, our logic, at every level of analysis. But if throwing an exception can cause Asio to stop making forward progress on an operation, why do we imagine that throwing an exception is the only way in which Asio can be induced to stop making forward progress on an operation? And as we think about this and we look at deployment experience with Asio, we realize this isn't just some arcane concern. The modal way that I have seen well-written working Asio applications effectuate shutdown is to simply stop calling run in the execution context. Let destructors run, never make forward progress on the operations ever again, gracefully clean up all of the resources and exit the scope. This isn't something Asio programmers do because they are bad programmers or they write programs that don't work. This formulation works perfectly in Asio applications. I've personally written multiple Asio applications which are probably running in production right now that exit in exactly this way. And so it's insufficient for us to handle just abandonment via exception. We need to handle abandonment for any other reason as well. And so maybe rather than iteratively discovering the whole problem domain, we take a step back and we look at the totality of it. We look at the outcomes of any asynchronous part of our Asio operation. Of course, in the happy case, the operation is finished and we don't need to worry anymore. In the slightly less happy case, we were just implementing one part of the overall asynchronous whole and the operation is still ongoing and we can deal with finalizing it later. Which brings us to what we were just reviewing. We were just reviewing exceptions, but then we noticed those brackets. We noticed that we've missed something, which is that we've only handled exceptions that come with abandonment. What if an exception is thrown and that does not indicate the asynchronous operation will no longer make forward progress? Imagine you have some high-level Asio operation and it's composed of two operations that it starts and allows to run at the same time. You run some asynchronous part, but of course that's only part of one of the sub-operations. It throws an exception. That sub-operation has been abandoned, but the total asynchronous operation hasn't been. There is still another outstanding operation, and so in this instance, it is unsafe for us to send set error immediately. Then we have that newcomer. We have just abandonment for no reason. We need to reify this as a new kind of completion signal by sending stood execution set stop to the receiver to indicate that forward progress has been abandoned. And so now we have to move on and we have to look at our code through a new lens. We previously wrote this code so assured that we were handling all of the edge cases. But what happens if this initiating function goes to initiate two operations that only throws on initiating the second one? There is still an asynchronous operation outstanding in the background, and so it would be inappropriate to finalize our wrapper in response thereto. And so all we can do at this point is hopelessly write down the fact an exception occurred and hope that maybe later we'll figure out what to do. Of course, we can't write the exception down if we don't have a member for it in the operation state, and so we do that. But that is not the only place we've reified this incorrect assumption. We've also done that inside of our executor in both of these places, and so once again, we simply write down the fact an exception has happened, throw our hands in the air, and hope that we're going to figure out how to deal with it at some point. But handling exceptions wasn't the only thing we introduced. We also introduced the idea of generalized abandonment, and so we provide some way for that to be communicated through the operation state. And then for reasons that will become only partially clear later in the talk, and unfortunately for Ben, I throw in a recursive mutex. But before we go off and we start using the operation state willy-nilly, we need to admit the fact that the operation state itself has a lifetime which is analogous to the lifetime of a regular synchronous stack frame. Anyone who's ever accidentally written a dangling reference knows that when you return from a synchronous function, the stack frame is cleaned up. And we've defined our asynchronous ecosystem by analogy to the synchronous domain, and so when we send a completion signal through to the receiver, that is like returning from a synchronous function. Thereafter, we can't depend on the operation state being within its lifetime. And so now we need to turn around and look at the outcome of every asynchronous step through the lens of what it means for the lifetime of the operation state. Previously, I said the operation completing was the happy case, but if the operation completes, we can't regard the operation state as being within its lifetime, and so we can't go inspect all of those needful members we've added, which journal the current state of the operation. But going down the slide, in the other two cases, it's critical that we do this. It's critical we determine whether or not the operation has been abandoned, but to do that, we need to look at a member of the operation state. Which brings us back to our diagram of our ecosystem, the way that our wrapper lambda invokes every single asynchronous part of the operation. Which brings us back to the analogy that I've been talking about, the analogy between the synchronous stack frame and an operation state. I'm up here obsessing about the lifetime of the operation state, but this wrapper lambda, which we need to communicate with to tell it whether or not the operation has been abandoned, is a synchronous function. It has a regular synchronous stack frame, and in that stack frame, it can store local variables with automatic storage duration. And so maybe it goes ahead and does that. It goes ahead and does that, but it tells the operation state where that variable is, so the operation state can now communicate with it in a way that is guaranteed to be within its lifetime when we unwind and inspect it. But this diagram on the slide isn't canonical. It's not the only possible call stack. We could have this reified reentrantly. What would we do then? Well, that upper wrapper lambda is also just a regular synchronous function. It has its own stack frame. It has its own variables of automatic storage duration. And so we just make an intrusive linked list. We let the operation state know where all of the states waiting on the outcome of the completion handler are so that it can go and it can communicate with them whether or not the operation is completed and whether or not it is safe or unsafe to regard the operation state. Let's reify this in some code. We go ahead and we create a frame type, and of course, since what I said earlier, we need to enrich our operation state with an intrusive linked list thereof. But that doesn't tell us what frame actually does, and so we go and we crack open frame, and we can see immediately that it derives from slist base hook, allowing it to participate in this intrusive linked list. It has a pointer back to the operation state, and this is critical. This is not a reference back to the operation state, it is a pointer. When we realize the operation is completed and it's no longer safe to access the operation state, we can set it to null and make it impossible for that to happen. Since we're guarding a state, we go ahead and we delete our copy and move operations, and we provide a convenience operator bool which allows our consumers to detect whether or not the operation has ended. Moving on, we have a constructor, but we don't just populate our self pointer, we also become a lock guard on the recursive mutex. Then, of course, we go and we add ourselves to the intrusive linked list in the operation state. The operation state, which needs to be able to notify us if the operation is completed and deactivate us. And so we provide a release function that does exactly this. We pop ourselves from the intrusive linked list, we unlock the mutex, and then finally we set self to null to ensure that it's impossible for us to go out and look at the operation state. But none of this answers the fundamental question for which we wrote this type, which is how do we know when we send exceptions and stop through to the receiver? And that logic is reified in perhaps the most complicated slide in this entire talk, which is the destructor of frame. If self has already been cleared, has already been set to null putter, the operation is already completed, and so there is surreptitiously no work for us to do. On the other hand, if we do have work to do, we go and remove ourselves from that intrusive linked list. We don't want to have a dangling pointer to ourselves. Then we compute whether or not we should be the ones to actually complete this operation, whether it is incumbent upon us to complete it to provide the guarantees of structured concurrency. If there are no frames left, we are the last person participating in the ecosystem. And so we check to see if we've been abandoned. If we have been abandoned, we are the last part of our ecosystem participating. If we don't finalize the operation, no one ever will, and we will have run afoul of the guarantees of structured concurrency. And so we release the lock and we check whether or not we should complete. If we should complete, we check for a stored exception. If we find it, we complete with an error. If we don't find it, we send set stop through to the receiver. But in doing this, we've done something that we've done earlier in the talk. We have enriched the set of ways in which our operation can complete. And so immediately we dutifully go back to transform signatures and we enrich it to document the fact that we also send set stopped. With this in mind, we can now go visit those pieces of code that we left behind earlier. We wrote down that an exception occurred, but we didn't understand what logic we needed to implement in order to send that exception through only when appropriate. But now we know exactly what to do. All we need to do is construct a frame object and let its lifetime end, and it will take care of everything else for us. Of course, this is not the only place that we did this. We also did this in our executor, and so now we simply go and create two local variables. But this isn't helpful if the completion handler isn't participating, because the completion handler is at the center of this. And so now we need to give it bona fide constructors since we want complicated logic to construct and destroy it. When it's created, it of course populates the pointer, but now we enrich the move operation so that only the most transitively derived completion handler has a non-null pointer to the operation state. This is completely acceptable because Asio only requires the completion handlers be movable. And so as the Asio operation moves it around, only the most recently created one will have a non-null pointer, will be controlling over the operation state. All of the other ones will be deactivated and their lifetimes can end without any consequence. Speaking of which, we actually need to implement that logic. And so in our destructor, we check the pointer back to our operation state. And if it is truthy, we may need to finalize. This is being abandoned. And so we construct a frame so when it goes out of scope, we'll perform the finalization logic. If any, we go to the operation state and we say that it has been abandoned. But this is all just scaffolding around the unhappy case. What about the happy case when the operation actually completes successfully? In this case, we acquire our lock guard, we go to the operation state, and we release every single stack frame currently participating in the ecosystem. We tell them they have nothing left to do as we unwind. With this done, we drop the lock, we grab a reference to our receiver, and we null the pointer inside of ourselves, thereby deactivating our destructor and ensuring the only way in which we'll complete this operation is on the very next line where we send stood execution set value through to the receiver. And in completing this, we've actually succeeded in projecting the guarantees of structured concurrency on top of the unstructured primitives of Asio. But that's a double-edged sword. The formulation I gave earlier for Asio, where you can just walk off and let destructors run, is convenient. If you decide you're no longer interested in the execution, you can just walk away and let destructors run. But structured concurrency doesn't just guarantee you that operations will complete, it also makes it incumbent upon you to wait for those operations to complete before you move on. This is how we're guaranteed that operation states remain within their lifetime for the duration of the asynchronous operations with which they are associated. But what happens if you start some operation and it runs for a long time and you decide at some point thereafter you are not interested in the results of that computation? You now have your hands tied by the guarantees of structured concurrency. Despite the fact you no longer care about that computation, you need to wait for it to complete anyway. Which brings us to the final piece of marrying these two ecosystems, the need to marry together the ways in which they reify cancellation. And fortunately, both of them support mechanisms for accomplishing this. In the case of stood execution, this is accomplished via stop tokens. A receiver carries along with itself an environment. We can interrogate that environment as to its stop token, and then on the stop token, we have two important basis operations. We can interrogate it as to whether or not a stop has already been requested, and we can use it to form an association between that token and an invocable, such that when a stop is requested, the invocable is invoked, and whatever action it reifies is taken eagerly. Asio, on the other hand, realizes this through cancellation slots and signals. A cancellation signal is emitted, and the corresponding cancellation slot then invokes whatever handler it holds, if any. With this out of the way, we can take a look at how we're going to glue these two ecosystems together. We, of course, start with the receiver, since that's what we receive from our consumer in the stood execution ecosystem. From that receiver, we can, of course, generate an environment. From that environment, we can source a stop token, and using that stop token, we can forge an association with an invocable known as a stop callback, such that we get to eagerly take some action when stop is requested. Of course, the action we can take can easily be emitting a cancellation signal into Asio, a cancellation signal which Asio knows about because we associate its slot with a completion handler. Let's take a look at how we actually reify this in code. Let's take a look at what we're going to have to add to our operation state to realize this. We have our invocable structure on stop request, and then, of course, we have a cancellation signal. Thereafter, we have an optional stop callback, a stop callback type synthesized by going to our receiver, interrogating it as to its environment, interrogating that environment as to its stop token, and then interrogating that stop token as to the type of callback that needs to be formed to associate it with our onStop request type. Which raises the question, of course, of what that onStop request type looks like. A simple invocable which acquires the recursive mutex and then emits a cancellation signal into Asio. And this raises the question of why we need this recursive mutex, and the answer to that is because Asio says so. Unlike stood execution, Asio says that if you thread unsafely emit a signal with respect to all of the other elements of the operation being canceled, you have undefined behavior. Fortunately, earlier in the talk, we wound this recursive mutex through every part of our ecosystem, and so while we hold it, we know we're not racing with any of the other asynchronous parts. We can emit the signal with confidence. But this is insufficient for us to glue these two ecosystems together because we're relying on the presence of a data member which is optional. And so we go back to the place where we initiate our operation and we enrich it with logic to populate that optional, to construct our stop callback by getting the appropriate stop token and associating it with an instance of onStop request. Note that here we take advantage of that convenience member of frame that lets us interrogate it as to whether or not the operation is already completed. If frame is falsy, star this may be outside of its lifetime, and so it would be inappropriate to go and regard its members. Otherwise, it is incumbent upon us to do this. But this raises the obvious question. Why am I deferring this construction? Why don't I simply set this up in my constructor? Why do I need to get optional involved? And once again, this is because Asio says so. Asio says that if you emit a cancellation signal into an operation before the return from its initiating function, that cancellation signal can miss and have no effect. All of the work that we did to ensure that we can stop operations to move on with our lives would be for naught as that cancellation signal sails into the abyss and the operation runs on untrammeled thereby. But of course, this still is insufficient because we still haven't published that cancellation slot out to Asio. And so we write an associator for the second time in this talk, associating our completion handler type with a cancellation slot. Our get member function simply goes to the operation state, goes to its cancellation signal, and returns the slot, thereby integrating this into Asio. But Asio isn't the only ecosystem that has arcane requirements. Stood execution has some arcane requirements of its own. Earlier, we discussed at length the asynchronous lifetime of an operation state. The fact we can only assume it's within its lifetime while the asynchronous operation is running up until the exact moment at which we emit a completion signal. And the standard also requires that we reify this with respect to stop tokens. We are only allowed to use the stop token associated with a receiver from the time start is called into immediately before we send a completion signal through to the receiver. And so if we want to reify this requirement as well, it is not only incumbent upon us to defer construction of our stop callback, we also have to eagerly destroy it before our operation completes. And so we go on a last-minute tour of all the places we complete our operation. We look at where completion happens and we simply enrich it by resetting the optional. Of course, we complete our operation from more than one place in our code, and so we go and look at the other place in our code and we similarly enrich it. Now we've actually completed all of the code that marries these two ecosystems. But where does that leave us? I started this talk out by showing you some example code, and then we went off and we explored the depths of the asynchronous models of stood execution and Asio. What does all of this mean for that code we were aiming at for the entire talk? The code that we actually want to make work, the ability to call all of those Asio operations natively from stood execution. And as we stare at this code, we notice there's a problem. We notice the way in which we initiate all of the asynchronous operations belies what we know from the talk. We know that initiating asynchronous operations requires a completion token, but we haven't stated one here. But as we go back to our setup code, we can enrich our understanding by knowing something else about Asio. When Asio selects a completion token, you can, of course, provide one explicitly. But if you don't provide one explicitly and the executor associated with the I/O operation upon which you're performing the operation has a default completion token, it will simply be used. And so we can take these I/O objects and we can rebind their executors to an executor which has our completion token as a default. Now we don't need to state it. We can simply call the asynchronous operation only with its needful parameters and have it use stood execution by default. Or at least we would be able to if we paid attention to the ways in which those operations complete. We notice those operations all complete in the idiomatic way Asio operations complete by sending a leading error code indicating whether or not the operation succeeded. Our integration blindly sends these down the value channel And the code we're aiming at, the code we want to be able to write, simply ignores them entirely, acts like they don't exist. It doesn't even compile as we've seen it so far. And that's because the completion token we've written is the bottom layer of integration between Asio and std execution. It only does the bare minimum to allow you to call Asio code from std execution. But what if someone decided they were going to slightly enrich our completion token? They were going to take all of the hard work we've done, and on top of that, put some generic programming such that they check the first argument, and if it's an error code, and if it's truthy, they do some special handling to send that down the error or stop channel. Because, of course, Asio errors can also encapsulate cancellation. Thereafter, it simply carves that argument off and sends the remainder as set value. Doing this would allow our code that we've previously seen to compile. We could put it into our compiler, we could try and run it, and we could see that it, of course, connects up to Google, submits a request, and prints out the response. But then sometimes it just sits there. Google doesn't close the socket. I don't actually regard the content length header, and so it simply hangs. I could stand in front of you and write an HTTP parser on the slides, but I don't know that would fit, and it would be even less germane to this talk than the I/O stuff we ignored earlier. And so instead, why don't we show off the power that we get from the structured concurrency and generic nature of std execution? Why don't we reach into our tool bag of Asio operations and say, hey, I want a steady timer. I want that steady timer to expire 1 second from now. I want to use a generic asynchronous algorithm to simply stop computation when either that timer expires or I complete reading from Google. This implementation of a timeout, which has stymied people writing asynchronous programs in C++ for so long, is now reified in a single line of code. So where does that leave you? I've gone to the end of the talk, and at the last possible minute, I've sprung some things on that you don't even know the code for. If you went home and you tried to write down all the code off the slides after I posted in Discord, you'd be left wondering how you actually implement as default on and how you can implement use sender. You would be posting comments on my YouTube video that look like this. Comments I've gotten previously when I wasn't able to release the code because it was part of a proprietary code base. I was only able to show what is on the slides. But this code is too important. The ability to leverage the 20 plus years of proven operations we have in Asio is true critical to be gated behind IP. And so I'm not here to tell you that you can use this code when I open source it on GitHub in a week or a month or when my manager approves it. I'm here to tell you that this code has been open source in NVIDIA's std implementation since May. You don't need to wait to use this. You can simply open your laptop right now, stop listening to me, clone std and start using all of the Asio operations we know and love using std execution right now. Because that is the conclusion of this talk. We have a newcomer. We have std execution. It's backed by theory. It's backed by claims that it is superior in terms of its structure and how generic it is. But those 20 years of history aren't going to go away. We're not going to rewrite all of our asynchronous operations that we have deployed in production and we know are working. But fortunately, std execution isn't the only flexible generic player in the game. The Asio model, iterated to across the course of 2 decades, is sufficiently flexible that we can customize it to implement all of the guarantees of structured concurrency. We don't need to wait for people to port their libraries. We can simply download a single repo and start using all of the history of asynchronous programming in C++ from the newcomer today. I have 11 minutes for questions.
Thanks, Robert. And the code being available is pretty awesome. That gives us a lot of things to look at, not just to be able to use Asio, but for the question that I have now. This seems like there were a lot of things that you had to really think about and consider. And part of it is because of just the complexity of both components that you're integrating. But if we have existing code that might not be using Asio, but might be doing asynchronous things, and we want to port it or integrate it with std execution and senders and receivers, are we better off just throwing it away and rewriting it from scratch, or can we use these lessons? Is there a pattern that we should apply in order to port our stuff over?
Yeah, so I think the pattern that's embodied in this talk and that applies to all forms of legacy asynchronous programming is basically that you can take any code you have that does asynchronous processing and you can reify it as senders and receivers if you can figure out a pathway to provide the guarantees of structured concurrency. Or you can decide that you don't care and you're willing to terminate your program willy-nilly. That's the hardest part, is the fact that because stood execution provides structured concurrency and because structured concurrency has such rigorous requirements, some legacy systems, it's very difficult to retrofit them to provide them. There's a lot of legacy systems where you start an operation and if it never ends, you're supposed to be fine with that. There's a lot of legacy systems where you don't use a proactor model, you use a reactor model, right? You sign up and you get a stream of events and it's unclear how to model that in stood execution. I think that modeling existing asynchronous code in a sender, if it's possible, is valuable because then you get the compositive power of senders and receivers, right? Like the structured concurrency thing isn't just people nagging you because you didn't do the thing that they platonically derived as being correct. It actually provides you the possibility to do things like say, okay, here's two asynchronous operations, both reified as senders. Complete when either of them complete, right? That's very difficult to model in a lot of existing asynchronous models, and it's something that's so confusing that in 2019, I gave an hour-long talk about how to do it in Asio, right? And then if you have the guarantees of structured concurrency, you just write when any, my timeout, my operation, and it just works, right? Everything underneath you provides the guarantees of structured concurrency. It obeys stop tokens, and so it just works top to bottom. And so I think adapting existing code is very, very important. I think that in a lot of cases, you may have a model that provides you some of these guarantees or all of these guarantees natively because they're valid, and wrapping them up into the lingua franca that you can use to talk to other people's asynchronous operations and use the standard operations is worth it. I know one common pattern is people use Asio as an implementation detail and they wrap it somehow. And I think that if they just provide a parallel interface that's a sender, they'll find that it's much easier for them to consume their operations, and they also have a lot fewer edge cases. One of the things that stood execution avoids that Asio suffers from is shared putters and ad hoc reasoning about lifetimes, whereas structured concurrency gives you guarantees. You don't just have some socket in main and then say, okay, well, I guess it's going to be alive for the entire time I'm running my application. You can actually use structured primitives like letValue to have that socket be part of the operation state that's outside of your asynchronous operation, and so you get all the same guarantees as when you call a synchronous function and provide it a reference parameter. That is, that it's going to live until you return from your function, or in this case, complete the asynchronous operation. Any other questions?
I have a couple of basic questions because I'm familiar with Asio, but not with the execution. So I got half of what was going on here. So the first one is if you abandon an operation, so you have an operation that's composed of two operations, and you throw in the first one and you abandon the second one. Can you give an example of of the danger of that? Would there be something if the second one ran, it would release a resource or something like that? Or?
Yeah, so a very common pattern that's impossible in Asio, but is extremely common in the kind of stood execution code people are writing, is that they do, in one of the talks I gave, I forget whether it was at CppCon or C+ Now this year, I have an example where I raw new a pointer, and then I call start on an operation state, which is guaranteed not to throw, and I just drop the pointer on the floor because the pointer is part of the state of the asynchronous operation. Because of structured concurrency, I know that operation will complete somehow, right? So the destruction that occurs at the end will happen. With Asio, I can't do that, right? If I raw new something and I want to pass that pointer into an Asio asynchronous operation, the completion may never run, right? I need to write ad hoc destructors and completion handlers. I need to use a shared putter. And so that's one of the big pieces of power you get from this is you're guaranteed the completion. And so you can do things like, Kirk Shoup has been working on the idea of an asynchronous object, which has an asynchronous constructor and asynchronous destructor. And you can't implement that in Asio because you don't know the asynchronous destructor will ever run.
Okay, that totally makes sense. And the second question is the motivation from a high level. You have Asio that's, for instance, running a web server or something like that, and you can use its output and connect it with asynchronous operations going to a database or something like that. Like what is the motivation for gluing these two systems together? So
the motivation for gluing them together, I think, is twofold, right? Like Asio provides a lot of really valuable fundamentals that we don't want to rewrite, right? Or if we do want to rewrite them, we want to make sure it's worth it, right? You go off and you use an Asio operation using its integration. Maybe you find it so hot that you don't want to pay the cost of this and you go and you rewrite it. But you knew that you needed to do that, right? But so we have all these Asio operations and we don't have a lingua franca for making them work together in the common structures that we want. Right, we end up writing things like ad hoc asynchronous loops, ad hoc asynchronous algorithms, Whereas with std execution, if you have two Asio codebases or two Asio operations, now the interoperation between the two of them can be modeled through std execution. For example, the example I showed at the very beginning, we had the async resolve, and that was piped into let value. And let value accepted the results and then used that to perform a follow-on async connect. You can do that in Asio, but the code becomes unmanageable as you do that at multiple levels of analysis. Whereas the sequence I showed, which isn't part of std execution, but is part of the extensions in NVIDIA's std exec, makes it simple. I write sequence, and I pass in a bunch of senders, and then when I start it, they're all going to run. I don't need to get into callback hell. I don't need to figure out and start reasoning about lifetimes. It's just structured concurrency, and so I have the same kind of guarantees I have if I just call 3 functions in a row.
So real quick, if you're always enforced a model where you have a single-threaded IO context, do you still need the mutex?
Right, so that, the recursive mutex, I have a work item. One of the last work items I have for the integration in std exec is to make the requirement for thread safety a parameter, right? So like if you know, like you say, as the modal Asio application I've worked on knows that every one of its IO contexts is single-threaded. And I say that because I have deployed applications in the past that fork out and spawn 16 IO contexts, but each one of them is thread safe internally. And so in that case, you don't need the recursive mutex. For now, the implementation in std exec pessimizes and always creates it and always acquires it. But it would be very possible to have a template parameter that says, don't worry about synchronization. I know my code is single-threaded.
Thanks.
I have a few more minutes if anyone has any other questions. Well, thank you very much.